Hello, everybody. So we're back with another lecture on some derivative rules, and these are going to be kind of the biggest rules that we're going to learn. They're a little different from something like the power rule in that these are not meant for a specific type of function, but rather functions that look a certain way. So we wouldn't say that these are rules like for a polynomial or for an exponential function or for a logarithmic function. But when we see a function of a certain form or written in a certain format, then we'll apply these rules. And these rules are going to be the product, the quotient, and the chain rules. So let's go ahead and get into these, and let's go ahead and look at the product rule first. So just starting off with some notation that we're going to see throughout this lecture, I'm gonna always be talking about a function that I'm going to call f of x. And when I write out that function, it's generally going to have two different parts to it. And those two different parts are usually pretty easily identifiable. And basically what I'm getting at is each of those parts is themselves their own function. So for example, I might have something like f of x is equal to x squared times e to the x. And if I see that, then I could say, hey, look, there's one part here on this x squared, and there's a second part here on this e to the x. So those are two individual functions, right? X squared itself is its own function, and e to the x is itself its own function. And so when we see all these examples of these functions f of x, what I'm going to do is I'm going to start labeling them with u and with v. And like I said, those are each functions themselves, so I'll call those u of x and v of x. Obviously down here in this example, I've done that color coding. The u of x I'd call x squared, and the v of x I would call e to the x. So that's just kind of an example there of function types that we'll see where there's sort of two distinct parts to the function. So if I have a function that looks like this, where it's two distinct parts, taking the derivative is not quite as simple as just taking a derivative of each part and leaving it like that, leaving them multiplied. We saw some properties last time where if I had two functions that were added, or if they were subtracted from each other, then I could just take a derivative of each of them and add those together. But it doesn't quite work when I have multiplication. So what we have to do is this funky thing called the product rule. And we use that word product because we're talking about multiplication. So if we have this format, f of x is a function that looks like u times v, two different parts, then if I decide to take a derivative of f, I'm going to have f prime, that's my derivative. And what I have to do is I have to do the derivative of u, so that first part, multiplied by the derivative, or multiplied, excuse me, by just v. I leave it alone. And then I add to that, leaving u just as it is, and then I take a derivative of the v part, that second part. So if I were writing out the derivative of this guy, I know that we haven't looked at the derivative of e to the x yet, but that's okay. We'll just not actually say what that derivative is. If I were taking a derivative of this, what I have to do is I have to take a derivative of the x squared. I have to multiply that by e to the x, just leaving it as just what it is, e to the x. Boom, that's my v. Then I add to that u, which is just x squared, and I don't take a derivative of it. And then I multiply that by whatever the derivative of e to the x is. We haven't actually talked about that yet. I won't even say what it is now. Just whatever the derivative happens to be, that's what you'd multiply that by. So let's go ahead and get into an example here. We're gonna look at this function f of x equals square root of x multiplied by 1 plus x squared. So when you see this, it should be pretty clear that there are two distinct parts to this. We have a root x, and I'll go ahead and mark that in red here. So I've got my root x, and then in orange I'll mark it, I've got my 1 plus x squared. And we can use the product rule on this because there's these two distinct parts. Now, also, just as a little aside, I don't have to use the product rule here. You could get clever and you could expand this out into you could distribute it, and you could have two different polynomials. And those would be pretty simple to take derivatives of with the power rule. That'd probably be a little easier, but just for the sake of this example, I'm going to actually do the product rule. So let's go ahead. I'll label this u, and then I'll label this V, and we'll remind ourselves of the product rule. So the derivative here is going to be u prime of x times v of x plus u times v prime of x. And also, just to be clear here, sometimes what some people do is they'll just write u prime v plus u v prime, just kind of saving themselves from having to write all of these x's out. We know it's a function of x, so we can just write u prime v equals, or excuse me, u prime v plus uv prime. So let's go ahead and go on here. Let's go ahead and plug things in. So in pink, I'll go ahead and do u prime of x. So this would be the derivative of square root of x. Notice I'm going to use that notation with a d dx because I haven't actually taken that derivative yet. And I'm going to multiply that by the orange v of x, which is just 1 plus x squared. And then I'm going to add to that u of x, which I'll write in red. And that's just my square root of x. And I'm going to multiply that in purple by the derivative of v, which is 1 plus x squared. And so I've got each of my 4 parts here, and we actually have to take some derivatives now. And so let's go ahead and do that. So this d dx of square root of x, hopefully we remember, let's do this off to the side here. Hopefully we remember that the derivative of square root of x is just going to be the same thing as the derivative of x to the 1/2, because I'm just rewriting that square root of x. And if I actually utilize the power rule, I'm going to get 1/2 from dropping that power down, and then I'm going to subtract 1 off of that 1/2 power, which gives me a negative 1/2. And if I simplify this, I'm going to get 1 over 2 root of x. And this derivative kind of pops up so often. We see the square root function often enough that I personally just memorize this work. You don't have to. I just think it saves a lot of time. Ooh, that white color doesn't look good. Let's go ahead and change that back. Let's change that to like, nope, not yellow. So yeah, so just as I was saying, that ddx of square root of x pops up so often that I always just remember that it's 1 over 2 root x. That's just something I like to memorize. Great. But while we're here, let's go ahead and fill this in, 1 over 2 square root of x. And let's do that in a different color as well. I'll match that pink color. And then I've got my 1 plus x squared plus square root of x, that hasn't changed. No derivative required there. Times the purple, and this should be a much easier derivative. The derivative of the 1 is just 0. So I won't even bother writing that. And the derivative of the x squared is just 2x. We've seen that before, and we can utilize the power rule there. So at this point, we're actually done with the calculus. We've taken our derivatives. Now it's just a matter of simplification. And so we can go through and we can just, simplify this guy as far down as we want to. That's a big thing that we like to do with these derivatives, is simplifying. So let's go ahead and copy this. I'm going to copy this onto a new page here. All right, so we've got all of that right there. Let's make this all one color as well. Great. So this is our f prime. Now it's just a matter of algebra and simplification. Let's go ahead and do this. I am going to expand or distribute this first term out. So I'm going to have a 1 over 2 root x plus x squared over 2 root x. So just some expanding out there. And then what I'm going to notice here is that I have a square root of x multiplied by 2x. So this is going to be x to the 1/2 multiplied by 2x. Let's go ahead and continue simplifying. Leave this 1 over 2 root x just like it is for now. I have an x squared over a 2x to the 1/2 plus, and now when I have x to the 1/2 times 2x, that 2 I can just bring out. That's a constant. That'll just pop right out. Now I have x to the 1/2 multiplied by x to the 1. So that's going to be x to the 1/2 plus 1, which is 3/2. So I have 2x to the 3/2 right there. I can do the same thing here on this second term where I can, because they're divided by each other, I can subtract the 2 and the 1/2 and I'll get x to the 3/2 actually again. So I'll have 1 over 2 root x plus x to the 3/2 over 2. And then I'm actually even going to go further and I'm going to rewrite this one more time as 1/2 x to the 3/2. So just a lot of rewriting and a bit of exponent algebra there. And this gets us basically down to our final answer here. 1 over 2 square root of x plus 5/2, excuse me, I almost said 3/2. It'd be 5/2 x to the 3/2, and that's all fine and dandy there. We could technically go further with this if we wanted to. I'm going to go ahead and leave it there for now. We'll see on the worksheets a lot of great examples of how to simplify all the way down. And so always keep that in mind, that when you have your derivatives, we want to write them as simple as possible. And so doing this work is necessary for these problems. Throughout the worksheets, you might get confused about, when do I stop? Take a look at the worksheet solutions to see that, to see sort of when I prefer to stop, when is a good time to stop with your simplifying and move on to the next problem. So that's a good example of the product rule. Just going back here, we've identified our parts u and v right there, and we've just done this formula that you'll use so often that you'll get it ingrained in your head, and you'll just know it as u prime v plus uv prime. Great. Let's go ahead and move on to the quotient rule now. This is all the work I already did, just skipping over that. So the quotient rule now, we've seen this example of the product rule where we have a function that's in the form of u multiplied by v. But now what if my function is of the form u divided by v? So what if it's one part divided by another? Well, the formula gets a little bit more complicated here. And this is it. You can kind of stare at that for a second. V of x, which is the bottom, multiplied by the derivative of u, which is the top, minus u, which is just the top, multiplied by the derivative of v, which is the bottom, all divided by v squared here. So that bottom square. And one way that I like to sort of memorize this or remember this is this little low d high minus high d low over low squared. For me, that's always just kind of stuck in my head as a tiny little jingle, a little tune that gets stuck in my head. If you choose to remember it that way, fine. If you choose to remember it in other ways, that's great. But looking at this here, I've got low, which is my v. And then when I say d high, that's saying a derivative of the top function, the higher function, u, minus sign, minus, high, which is u, d low, which is a derivative of the lower function, v, over, that's my fraction bar, low squared, so that lower term v squared. So low d high minus high d low over low squared, that's kind of a fun way to be able to remember this quotient rule. So again, let's go ahead and look at an example here. I've got f of x equals 2x plus 1, all divided by 3x minus 4. And if I go ahead and identify my parts here, I'm going to have my 2x plus 1 as u. and I'll just write u rather than u of x because we know it's a function of x. And I've got my 3x minus 4 equaling v. So if we go through this and we actually write this all out, we can do our formula. So let's go ahead and write u equals 2x plus 1. Let's write v equals 3x minus 4. Let's take derivatives of these. 2 and 3, right? Those are just lines, so we get that slope, that derivative just right off the bat, just using the power rule right there. So at this point, I'm pretty much done. I just have to plug into our formula that we have back here. Let's go ahead and copy this guy so we can see it on our next slide. All right, so here we've got our formula. And remember, we have our uv, our u prime, and our v prime. So let's go ahead and copy that over as well. I'll make sure to separate these out a little better. Let's go ahead and great. So we've got our little grid of u, u prime, v, and v prime. And so let's just go ahead and plug into this formula here. So f prime of x is going to be v, which is 3x minus 4, multiplied by u prime, which is 2, minus u, which is 2x plus 1, times v prime, which is 3, all over v squared, which is 3x minus 4 squared. And so right here, we've got our derivative. At this point, we are done with the calculus. We can just simplify now, just a bit of algebra to actually simplify, and then we're done. So let's go ahead and copy this guy onto a new page, and we'll actually do that that calculation. All right. So we've got this there. Change the color here, something a little bit easier to see. So now our algebra comes along. Let's distribute out this 3x minus 4 on that 2. We get 6x minus 8. Minus sign, I'm going to put some big parentheses here because we always want to make sure that we distribute that minus sign appropriately. When I do my 2x plus 1 times 3, I'm going to get 6x plus 3. And this is all over the denominator squared. I'm going to leave that written that way. Expanding it out would honestly just make things look a little bit more ugly. And it would just be more terms to write, and that's just a little ugly. It's a little less simple. So here we've got 6x minus 8 minus 6x minus 3. That's me distributing that minus sign. And now I see here that these 6x's cancel, and my minus 8 and my minus 3 will combine. Oops, sorry, erased a little incorrectly there. Let's put that back in. There we go. Those 6x's are gone. So minus 8 minus 3 would be negative 11 over 3x minus 4 squared. That's after my 6x is canceled. At that point, we're done. We've got our answer. This is about as simple as you could make it. Like I said, expanding out that squared term on the bottom would probably just make things look even uglier than they already are. So we'll just leave it right like that, and that's our final answer right there. So that's a quick application of this quotient rule right here. A much more complicated formula than the product rule, but just as simple to plug in and do. So we're always starting off with that u and v and u prime and v prime right there. Let's move on to the chain rule here. So the chain rule is probably the most complicated to think about in these sort of derivative rules. And it all has to do with a composition of functions. So we're going to use this when we have an inside function and an outside function. And what gets tough on these chain rule problems is actually figuring out which function is on the inside and which function is on the outside. So before I actually explain this formula, let me show you an example of a function where we would use the chain rule, and then I'll come back to this formula and kind of explain what's going on. So here we've got a function that's x squared minus 3x all raised to the fifth. And this is a perfect time of using the chain rule because I have an inner function and an outer function. And that inner function here, I'm going to note as being x squared minus 3x, right? And then my outer function is going to be this fifth that's up here. Because basically what I'm doing is I'm taking this red function, and if you will, I could sort of box this and I could just cover it all the way up. I don't really even care what's on the inside there. This is just a big red blob. And that's my inner function. And what I'm doing to that is I am raising that to the fifth. So that raising it to the fifth is my outer function. That's the thing that I'm doing to this red x squared minus 3x. And so this is a perfect application of the chain rule. What I would say here is that my inner function, I've said this a couple times, but that's x squared minus 3x. And my outer function, well, we've said it's this to the fifth. So basically what I'm going to do to be simple is instead of calling it like, red blob all to the fifth, instead of writing red blob, I'm just going to write x to the fifth. And so that's my outer function. It's just me taking whatever is inside of it and raising it to the fifth. And just to be simple, I'm going to call what's on the inside just x, just giving it a placeholder name. But let's go ahead and go back here to this format on what we actually do. Now that we've sort of seen an example here where we can identify what's the inner and what's the outer part, let's actually go to this chain rule here and talk about what we actually have to do to take this derivative. And so we see here, I've got u, which is a function, and v is my input to it. So remember composition of functions. V is my inner function here, and u is my outer function. If I come back over here, if I were to write out u of v of x, I would be writing u of x squared minus 3x. And if I say that u is equal to that x to the fifth, that just gives me my x squared minus 3x all to the fifth right there. And so this is exactly just that composition of functions that we've seen in algebra before. So when you have that format, you're going to take a derivative as such. We're going to first take the derivative of the outer function. So u is that outer function, and I'm just taking a derivative there. I have u prime. So I take a derivative of that outer function, and I'm leaving the inner function untouched. I'm leaving it just completely ignored. I just copy and paste it as I would normally. I then multiply that by whatever the derivative of the inside function is. And I don't even care about what the outer function is in this portion of the problem. So that you're probably sitting there thinking, okay, well, what the heck? What did you just say? How do I even do that? Let's do this example and go ahead and follow it carefully. So we'll copy this over. Let me erase some of this stuff in the blue here. So I've got my inner and my outer functions. I've got my formula here. So let's follow this formula carefully. F prime of x is going to be u prime of v of x. And so like we said, u prime, u is that outer function. I'll label that there. And v is that inner function. So I'm taking a derivative of u, but I'm leaving v untouched. So that outer function is that x to the fifth, right? When I look up here, that outer function is this part. So I've used that word leave the inside. I've used that word untouched a couple times. I'm going to leave this x squared minus 3x, just pretending that it's a big giant blob and I just don't even really care about it. And actually, let's just go ahead and cover it up because I really don't. For right now, I don't care what's on the inside. So when I see this outer function, this raised to the fifth, this blob raised to the fifth, I look at that and I go, hey, this is a great example of the power rule right here. Power rule, because it's just something to the fifth, right? So what I'm going to do is I'm going to drop that 5 down and I'm going to subtract 1 from it right there. And let me write that in a different color there. I'm going to drop that down. I'm going to subtract 1. And so when I take my derivative here, I'm going to have 5 times my big red blob all raised to the 5 minus 1, which is just 4, right? So, you know, you can see this as if I had x to the fifth and I took a derivative, I would have 5x to the fourth. Now all I'm doing is I'm just basically saying, hey, my inside, the inner part, it's a little bit more complicated than just an x, but I don't care. I just leave it. It's just this red blob that I just leave it as it is. And so all I'm doing here is just this first part right there. I'm just doing that outer derivative. But obviously I do, now that we're kind of done, I do care about what this red blob actually is. And so I actually should write it in and we'll just leave it there. It's an x squared minus 3x. And so at this point now I need to do the second part of the chain rule, and that's this multiply by v prime. Well, when I see v prime here, I look at, or excuse me, when I see v, I can calculate what my v prime actually is. And so I see my inner, that v is x squared minus 3x. We can do a simple application of the chain rule to get 2x minus 3. And at that point here, honestly, we're kind of done. I mean, there's not really a whole lot more simplification I could do. If you wanted to, you could write it like this. Maybe this looks a little bit neater. It's definitely not changing anything. I'm not actually doing any simplification. But this is about as simple as you can make it. There's not really a whole lot more to do here. And so this idea of the chain rule, just as a recap, it's taking a derivative of the outer part and then multiplying it by a derivative of the inner part. But you just have to remember that when you do that outer derivative here, before you multiply it by the inner derivative, you have to just leave the inner part untouched here. And so I'm seeing this 5, x squared minus 3x raised to the fifth. So I'm basically ignoring this inner part. I'm just taking my derivative here using the power rule like expected, and then I'm just multiplying by that derivative of the inside. So let's go ahead and let's do one more example here. I'm going to make this up off the top of my head here. So let's say that we had a function f of x is equal to the square root of x squared. Let's use the same one, x squared minus 3x. So here I see an inner function of the x squared minus 3x, and I see an outer function that is the square root. I'll just go ahead and write that over here because there's not really a part to circle in the function. So the outer function is that square root. So all I'm going to do is I'm going to say, okay, well, let's take a derivative of that outer function. And the outer function is just a square root. And remember, we saw that d dx of square root, remember, this is that derivative that I said I like to memorize just because it pops up so often. It's just that 1/2 square root of x. So if I take a derivative here I have to utilize the chain rule because I have an inner and an outer part. I'm going to take the derivative of the outer part first, which is that square root. And so I'm just going to say, hey, it's 1 over 2 root whatever the inner function is. I leave that inner function untouched. But then the chain rule also tells me that I have to multiply by the derivative of that inner part, which is that 2x minus 3. So this right here is derivative of inner part. And then this other part over here, let's go ahead and change the color here. Let's match all those up. This is the derivative of the outer part, leaving the inner part untouched. Right there. And so we've just got our outer and our inner right there. Yeah. Great. And so that's just another quick example. Obviously, I could do some more simplification here on this part right here on this guy. I'm not going to worry about that for this example. We'll just leave it like that for now, just to kind of get a sense of how we use that chain rule in an inner and an outer part. Awesome. So that's pretty much it in terms of lecturing. Just a quick recap of these 3 rules. We've got the product rule, which says that the derivative of my function, and let's be clear here as well, our function f of x equals u times v. Here it would equal u over v, and here it would be u of v. I'll put an x there just so we're clear. U of v. And so my product rule is going to look like u prime v plus uv prime. I have to take a derivative of one, I leave the other, and then I add to that just the first one and the derivative of the other. So I kind of taking a derivative of each part separately, leaving the other part untouched, adding those together. Quotient rule, we've got our low d high minus high d low. That's not many other ways to really remember that. Just there's your formula. You kind of got to just plug and chug. And then we've got the chain rule, which is the derivative of the outer part multiplied by the derivative of the inner part. And when I do that derivative of the outer part, I leave that completely untouched on the inner part. I just don't change it at all. And those are our 3 rules. So we're gonna deal with a lot of these rules in the context of polynomials and simple functions like that for now, and then we'll make them a little more complicated in the future. But let's go ahead and wrap it up there.